The pattern is an element plus a compound. It's an A plus BX type pattern. So all these element plus compound, are going to be redox. For the test, I'm thinking I'll do the redox for the next exam. So that's going to make the homework a little bit tricky because I'm not going in the book's order. And so what we're going to cover for the test is metathesis and acid base. Redox will be the next test. And so I'll cover these for the next. I'll cover these today. So we're looking at metathesis reactions and a specific type of metathesis reaction. This metathesis reaction follows a pattern. What is the pattern of this? The double replacement pattern. What does the double replacement pattern look like? Yeah. So it'd be compound AB plus compound CB. These are typically ionic compounds because what we're going to do is we're going to just swap the anions. So this would be AD plus CB. Just swap the anions. This is different than this pattern up here. These are our predicted products, but we aren't going to get a reaction if there's no driving force. So what are the driving forces for double replacement reactions? Yeah. There are three. Stronger acid to weaker acid. That's one. Gas formation. And one more. Hope you guys write these down? Too much? If you write it down, how many times have you looked at it? Many times? If many times, it should be faster to recall. But a lot of people, you realize this, a lot of people, they look at it once and then they look at it maybe one more time right before the test, like the night before the test or the day of the test. And, it's hard to recall sometimes. They can get it in the short term. But hopefully you looked at it every day, over the break, the weekend. If you look at it every day, then it'll be easier to recall. Insoluble solid, or PBT, precipitate. And so, yeah, you want these to complete for the driving force. So we saw, last time we saw a driving force of the precipitation, the stronger acid to weaker acid. Let's just take a look at some more examples of this. Let's say if we take calcium carbonate and sulfuric acid. If we take calcium carbonate and sulfuric acid, what's the formula for calcium carbonate? CaCO3. And sulfuric acid? H2SO4. then we'll figure out the states for it. What's the state for calcium carbonate? Yeah, carbonates are insoluble except for group 1 and ammonium. This is not a group 1. Group 1 would be sodium, lithium, potassium. Ammonium is NH4, so neither of those. So this is insoluble, it's a solid. Sulfuric acids, those are group 1, so it's soluble. Hydrogen's in group 1. Not all acids are soluble, however. This one is. All right, so this follows the pattern. This is an AB plus CD type pattern. You know, A is going to be the calcium ion, B is the carbonate ions, C is the hydrogen ions, D is the sulfate ions. So what we're going to get is calcium sulfate and hydrogen carbonate. So calcium sulfate, what's the formula for that? Yeah, CaSO4. And hydrogen carbonate, what's the formula for that? H2CO3. Carbonate's a 2 minus, so we'll need 2 H pluses. We've just got to make sure we get the ratios correct here. Then this is our pattern AB plus CD, and then we look for driving force. Is there a driving force for this? First, we look for a precipitate. Is there a precipitate? So we go sulfates. Sulfates are all soluble, except for which one? Silver, lead, mercury. This one you probably have to repeat more than a few times. Silver, lead, mercury, calcium, strontium, barium. You just keep repeating it. Then you want it to come automatically, so that, you know, sulfates are all soluble except for silver, lead, mercury, 1, mercury 2. You know, calcium, strontium, barium, those are fixed charge, plus 2. So, good. Lead 2. And so this is actually a solid, an insoluble solid. But there's a problem with this particular one, and we'd like to say that there's a precipitate that forms. You know, it looks like a precipitate. However, this is tricky because what we're doing is we're going from one solid, because calcium carbonate is an insoluble solid. So what we have to do is we have to dissolve one solid to form another solid. And so this is called a solid to solid conversion, or solid to solid. So say solid to solid. So it's not just a straight precipitation. If you look at like a typical precipitation, in a typical precipitation we go from aqueous to solid. So if we go aqueous to solid, then definitely we're getting solid formation. But in this case, we have to sacrifice one solid to make another solid. Is it worth the sacrifice? And so what we need here is further analysis that has to be done. The further analysis, this comes in Chem 1A and Chem 1B. Probably primarily Chem 1B. And so I don't know if it's worth it or not to get rid of this solid and replace it with this solid. It depends on which one's more stable. But we don't need all three driving forces. We only need one driving force. And so, do you see another driving force? Yeah, the acid. If you look at it, this one's called sulfuric acid. This one's called, I call it hydrogen carbonate, but we should call it what? What's the name of this acid? Carbonic acid. So we're going from sulfuric acid to carbonic acid. So this is stronger acid. This is a weaker acid. But there's one problem with this acid. What's the problem with this acid? Well, what do you need to have memorized about this acid? Something you got to memorize about carbonic acid. Yeah. Yeah, it's unstable, so it's going to decompose into H2O liquid and CO2 gas. So we got gas formation. So all we need is one driving force. And so even though it was inconclusive, we're sacrificing one precipitate for another. That's inconclusive. But we do have weaker acid and we do have gas formation. So we have driving force. If we have driving force, then this reaction should go. And so this would be the CE, or the complete or conventional equation. And then we'll do the IE. The ionic equation, you have to ionize the strong electrolytes. And so what are the strong electrolytes? Strong acids, soluble salts, and strong bases. So calcium carbonate, is that a soluble or insoluble salt? It's insoluble salt, so we leave it alone. Just soluble salt. Sulfuric acid. What's that? Sulfuric acid is a strong acid, and so we ionize it. What does sulfuric acid ionize to? Well, I ionized it over here, H plus and sulfate. However, when we ionize it for this, only one hydrogen breaks off at a time, so we're going to get H plus HSO4 minus. Now, the second hydrogen, does it break off? Well, it depends. If HSO4 minus is a strong acid, the second hydrogen breaks off. If it's not, then it stays on. And so is HSO4 minus one of the 7 strong acids? No. This is a weak acid. Weak acids, would be the major species here, so I'll leave it like that. And then this is going to go to calcium sulfate. Is calcium sulfate a soluble salt? No, it's an insoluble salt, so leave it alone. And then water. Strong acid? No. Strong base? No. Soluble salt? No. So just leave it alone. And then CO2 gas. Strong acid? No. Strong base? No. Soluble salt? No. So we leave that alone. That would be the ionic equation. It turns out this is balanced. I didn't have to do anything to balance it. Now, for the net ionic equation, we get rid of the spectators. But are there anything, any species, is there anything that didn't react? No, everything reacted. So the ionic equation and the net ionic equation are the same thing. No difference. Another one. Sulfuric acid and sodium hydroxide. All right, why don't you try that one and see?